Welcome everybody to today's Bluetooth LE Mesh webinar. My name is Sven Hegner and I've worked for more than 17 years at Toshiba in various roles ranging from IC development, business development and standardization to technical marketing. For the past 4 years, I focused on developing MCU and Bluetooth-based solutions for innovative markets like wearable devices, smart home and smart building. I'm currently responsible for Bluetooth products at Toshiba Electronics Europe. We will start the webinar by looking at the current challenges that need to be addressed. Then we will take a look at the new Bluetooth Mesh extension, which was published in July 2017. I'll introduce a new topology option to you and highlight its major features and benefits for users. Afterwards, we will look at some application examples in which Bluetooth Mesh can offer many advantages. Finally, I will share information about Toshiba's Bluetooth Mesh solutions and with you, and then you will get an opportunity to ask questions. Low-power wireless connectivity is used in many applications, like home and building automation, industrial automation, lighting, asset tracking, home appliance, and many more. The main hurdle in home and building automation is that the market is extremely fragmented. According to IHS, there are 13 different standards plus a number of proprietary technologies based on sub-gigahertz radios. This fragmentation leads to several challenges. Customers are confused by the vast technology choices and hence hesitate to invest, as it's unclear which technology is best for them. Subsequently, they tend to delay their investment decision and wait for one standard to dominate the market. Furthermore, using different wireless connectivity for each system hinders interoperability and therefore may miss out opportunities for synergy effects. For example, when systems for heating, lighting and shutter control cannot interact with each other. A similar problem may arise even when the same wireless technology is used, but vendors implemented only a subset of the optional features or used vendor-specific extensions. Also, different interpretations of specifications can lead to interoperability issues. Wireless technologies that are not available in smartphones or tablets require bridges, as the communication takes place via Wi-Fi. In case of proprietary sub-gigahertz technologies, often dedicated remote controls are used, which add cost and is yet another item to clutter the home. Another challenge is the long-term availability of products using the chosen wireless technology. Certain technologies may not be available in the future because the market may have moved towards other wireless interfaces. Furthermore, new versions of standards may no longer be backward compatible with existing equipment. Last but not least, using dedicated closed solutions also requires a dedicated smartphone app for each system. In the past, Bluetooth LE only supported two types of topologies, one-to-one and one-to-many. One-to-one communication is used in sports and fitness applications, for example, to connect the smartphone with a smartwatch or fitness band. In health and wellness applications, a smartphone could be connected to a blood pressure meter. An analogy to one-to-one communication is that two persons that live in the same area communicate to each other via a telephone line. An example for one-to-many communication is a beacon that sends information to all smartphones within reach. Typical applications include indoor navigation, location-based advertising used by a store or restaurant, as well as trackers and luggage tags that help finding lost keys or luggage. An analogy to one-to-many communication is a person that uses a megaphone to distribute his message into the neighborhood. Since the advent of Bluetooth Mesh, a new topology for many-to-many communication has been introduced. There are two aspects. First, it allows multiple nodes to communicate to each other in a mesh network. Second, the communication range is extended through relaying a message via one or more relay nodes. An analogy is that multiple persons from around the globe participate in a conference call. However, there is a challenge. If these people want to talk to each other, they need to be able to speak a common language. Otherwise, it is impossible for them to exchange information. This common language is the Bluetooth mesh models. These models are specified by Bluetooth SIG, and they define data models for certain applications like lighting control, sensors, and generic data models like an on-off switching functionality. Standardized and compliant data models are required for true interoperability among products from multiple vendors. Bluetooth Mesh is a software extension to existing Bluetooth 4 and 5 hardware. The mesh network layer adds the mesh topology to allow the many-to-many communication. Furthermore, this layer contains mesh network management functions. On top of the Bluetooth mesh networking layer, there is the Bluetooth mesh model layer, which adds data models in order to enable interoperability across vendors. The benefit of only adding software layers is the ubiquity of available smartphones and tablets that have been already shipped with Bluetooth 4 and 5 connectivity. This means that right from the start, there are billions of existing smartphones and tablets available that may be upgraded with Bluetooth Mesh functionality. And every year, 3.4 billion interoperable Bluetooth devices are shipped, and a study revealed that 92% of global consumers are aware of the Bluetooth brand. As the underlying Bluetooth technology is unchanged, there is a very mature ecosystem for product development available. For example, mature development and test tools. In addition to this, there is a large network of companies that offer development, test, and qualification services. The focus of Bluetooth Mesh is on global interoperability. Therefore, 2 years of interoperability testing have been done before the standard has been made publicly available. In total, there were 15 interoperability test events before specification release. They are called Unplug Fests. In order to enable interoperability, test and qualification tools are required. Bluetooth SIG has developed qualification tools and processes over the last 20 years, and 17,000 new interoperable Bluetooth products are launched every year. Another very important key for interoperability is a full stack solution. This means all layers are standardized by Bluetooth SIG, in particular physical layer, network layer, and application layer. Interoperability also includes backward compatibility with older generations of the standard. Therefore, all Bluetooth mesh models are immutable. This means once a model has been adopted and published, it will never change to keep backward compatibility. Bluetooth Mesh uses a publish and subscribe paradigm. It is very similar to hashtags as they are used, for example, in Twitter. There, a person can publish a message to a certain hashtag, for example, hashtag Bluetooth Mesh. Other people who are interested in this topic can search for that hashtag and get all messages that other people have posted to that hashtag. In a building scenario using Bluetooth Mesh, nodes can publish their messages to a certain address. Other nodes that are interested in receiving these messages can subscribe to this particular address. For example, a light switch can publish an on-off message to the group address of the hallway. Light bulbs that are subscribed to the publishing address hallway can receive these messages and act on them. One or more subscriptions per node are possible. For example, a light bulb may be subscribed to the groups bedroom, upstairs, and house. In addition to interoperability, reliability is the second focus area of Bluetooth Mesh. Similar to how the Internet achieves its reliability, messages can take multiple pathways from the sender to the receiver. If one node breaks, messages can take a different route. This behavior is shown in the picture on the right-hand side. Messages from the light switch in the top can either be transferred via the left route or the right route. Many other low-power wireless technologies make use of a router, hub, or bridge. All communication from one node to another goes via these devices. If a router, hub, or bridge breaks, there's no communication within the network possible anymore. Therefore, such devices present a single point of failure. As the propagation of messages through the Bluetooth Mesh network does not depend on predefined routing channels, messages can take any path to their destination. If a node breaks and there is any alternative path around it to the destination, messages will automatically take one of these alternative paths. As this is done without any corrective action, we call this feature self-healing. Current home and building automation systems often use a centralized control. If, for example, a person uses a light switch, this information is first communicated to a central control system, which then decides what action this trigger invokes. For example, certain light bulbs are turned on. The downside of this approach is that the centralized control unit also presents a single point of failure, and multiple messages need to be sent back and forth, which may increase latency. Bluetooth Mesh supports distributed control. This means that, for example, a light switch can directly communicate to a light bulb in order to turn it on or off or change the color of the light. By this, Bluetooth Mesh eliminates the before-mentioned downsides of centralized control architectures. In a picture on the right-hand side, this is illustrated by the arrow in the middle between the light switch and the light bulb, although it doesn't necessarily need to be a direct connection. The third focus area of Bluetooth Mesh is scalability. There are two aspects. The first is scalability in terms of number of nodes that can be added to a mesh network. The second aspect is the scalability in terms of physical range and area that can be covered by a mesh network. As for the first aspect, Bluetooth Mesh network sizes are scalable from only a few nodes to all the way up to 32,000 nodes, which is the upper boundary that is supported by the standard. However, in practice, the maximum number of nodes is also determined by other factors, such as the available bandwidth to transport data generated by all nodes and also latency requirements. One way to conserve bandwidth in a mesh network is to keep data traffic more local by establishing subnets within a larger mesh network. These subnets may contain hundreds of devices. In real-world scenarios, Bluetooth Mesh networks with over 1,000 nodes are already in commercial use. As for the second aspect, in contrast to previous one-to-one and one-to-many topologies, messages in a mesh topology can hop from one node to the next in order to travel longer distances. Nodes that have the capability of relaying messages are called relay nodes. Each message can be relayed up to 127 times, and by this, Bluetooth Mesh also realizes a scaling in terms of physical distance and area that can be covered. The fourth, and arguably one of the most important focus areas, is security. The Bluetooth Mesh standard is one of the latest published mesh standards available and hence incorporates protection against the latest security threats. All messages within the network are encrypted and authenticated using AES-CCM with 128-bit keys. The emphasis here is on all messages. There are no unencrypted and unauthenticated messages within the Bluetooth Mesh network once the network has been set up. Furthermore, implementation of security features is mandatory for all Bluetooth Mesh designs to maintain a guaranteed high level of protection. In the past, other standards made some security features optional, which led to some implementations that did not make use of those options for cost reasons. However, those devices may compromise the security of the whole system. By mandating the implementation, this cannot happen with Bluetooth Mesh. Each mesh packet is obfuscated to remove any identifying information from a message. This prevents others from tracking mesh devices, especially when those devices move within range of other networks. Bluetooth Mesh supports multi-layer security. This means that there are 3 different keys: a device key, a network key, and 1 or more application keys. Each node within a network must possess the network key, otherwise they are not able to communicate with other nodes in the network. Application keys can be used to protect messages from one application to be accessed by another application. For example, if a smart door lock is in the same network as a light bulb, they share the same network key, but messages to the door lock are additionally encrypted with a dedicated application key, so that the light bulb may relay messages to the door lock, but it is not able to decrypt, modify, or generate messages in which the door lock is the initiator or recipient. Provisioning is the act of adding a new node into a Bluetooth Mesh network. It involves assigning a network address and providing key material to the newly added node. By definition, an unprovisioned node does not possess the keys for a secure connection. Therefore, Bluetooth Mesh makes use of a technique that is called elliptic curve Diffie-Hellman, or ECDH for short. ECDH allows to securely share keys over an unsecured link, so that it can be assured that only the new node will be able to receive the key material. In the past, certain applications couldn't be covered by Bluetooth one-to-one and one-to-many topologies. The many-to-many topology that comes with Bluetooth Mesh opens up a whole new field of new applications that can now make use of Bluetooth connectivity. One of the first and most promising applications in home and building automation is lighting control. In the future, it is expected that other applications like shutter control, sensors, heating, ventilation, air conditioning, access control, and the like will follow. Another new application is asset tracking. Here, Bluetooth Mesh with its scalability in terms of nodes and also covered area really shines. In particular, since Bluetooth Mesh modules for asset tracking are often battery powered and Bluetooth Low Energy has been particularly designed to run from small battery capacities, such as coin cells. The Industry 4.0 revolution comes along with a large amount of new sensors to provide much more insight into industrial processes. As these new sensors will often be added to existing machinery, wireless connectivity has a lot of benefits compared to installing new wires. Also, wireless sensors provide much more flexibility when the setup on the factory floor changes. High reliability and security are key criteria for industrial applications, and as explained earlier, Bluetooth Mesh is particularly well prepared to fulfill these requirements. Last but not least, usage of beacons for indoor navigation, location-based services, and heat map generation is on the uptake. More and more beacons are rolled out in public areas like shopping malls and train stations. However, managing these beacons becomes more and more challenging. Bluetooth Mesh can help to address these challenges by putting all beacons into a mesh network and therefore make it easy to maintain all of them from one point within the network. As beacons are already using Bluetooth Low Energy hardware, the existing resources can be reused. No additional hardware is necessary to manage them. By now, we have familiarized ourselves with a basic understanding of what Bluetooth Mesh is and where it can be used. Let's now have a look at the Bluetooth Mesh solutions that Toshiba is able to offer. The central part is the Bluetooth hardware with the necessary Bluetooth LE and Bluetooth Mesh software stacks. Every part has been developed by Toshiba and hence fits seamlessly together. In addition to the Bluetooth Mesh 1.0 stack, we also provide a reference implementation of the HSL lighting control mesh model. HSL is a certain color model that has been designed by computer graphic designers, researchers in the 1970s. HSL stands for hue, saturation, and lightness. On the smartphone side, we provide a reference application for Android, which allows to add new nodes to a mesh network and to comfortably configure them. For example, the relay capability can be enabled or disabled via a simple button in the app. Furthermore, lights can be switched on or off, and the color of the lights can be chosen graphically. On the board side, Toshiba developed a Bluetooth LE mesh lighting reference design, which mainly contains a Bluetooth module and a multicolor LED. This board represents one lighting node. The reference model can be used by customers as a starting point to design own products. All design sources can be made available to customers. In addition to the lighting reference design, Toshiba also developed a smart plug reference design using Bluetooth Mesh. A smart plug sits in between a wall outlet and a plug of devices, such as a floor lamp. There are basically two features. One enables the switching of the attached device on or off via Bluetooth Mesh network. The second feature measures the power consumption of the attached device and distributes this information back to a smartphone or other device through the mesh network. The benefit of this reference design over existing smart plug solutions is that it is able to directly communicate with a mobile device like a smartphone. Zigbee and sub-gigahertz based smart plugs always require a gateway, which presents a single point of failure, as we have learned earlier. Even Wi-Fi based smart plugs need to communicate via a router and hence suffer from the same risk. Bluetooth point-to-point solutions do not require a gateway, but they are not able to communicate with many smart plugs simultaneously. The connection to a plug may need to be broken up in order to establish a connection to another plug. However, with Bluetooth Mesh, all smart plugs can be part of the same network and so can be accessed simultaneously. It is even possible to create groups and scenes. As smart plugs are always mains powered, they are perfectly suitable to be used as relay nodes, and so help to build an in-house Bluetooth mesh infrastructure. The current mainstream product is our Bluetooth Low Energy 4.2 controller. Its part number is TC35678. It comes with an embedded ARM CPU and 192 kilobyte of RAM, of which 83 kilobyte are available for user applications. In addition to the RAM, there is 256 kilobyte of integrated flash memory available. One of the key differentiators is the industry-leading low peak power consumption, which makes this chip among the best choices for battery-powered applications and other applications in which low power consumption is crucial. Both the receiver and transmitter have a peak current consumption of only 3.3 milliampere. In deep sleep mode, the whole chip consumes less than 100 nanoampere. And, by the way, this feature is also true for usage in traditional one-to-one and one-to-many applications. Many new features that have been introduced to the Bluetooth Low Energy standard after version 4.0 are optional. While some of our competitors only implemented a subset of the optional features, Toshiba decided to implement all of them to provide the highest flexibility to our customers. These features include early data packet length extension, early secure connections, link layer privacy, link layer extended scanner filter policies. The detailed explanation of each feature is a whole other conversation, which is outside of the scope of today's webinar. Another major benefit of Toshiba's Bluetooth Low Energy solution is that most of the external components are already integrated into our chip. Only 7 external components are required, which is much less than some other solutions on the market require. Benefits for customers include a lower bill of material cost, as fewer external components need to be purchased and placed on the PCB. Even the RF matching circuit is integrated, which has the additional benefit of reducing development effort and time, and hence reduce time to market. As you can see in the table on the right-hand side, only one inductor, 4 capacitors, and 2 crystals are required for a complete Bluetooth LE implementation. As mentioned before, Toshiba's Bluetooth IC offers industry-leading low power consumption. In order to relate this information to a practical real-world scenario, Toshiba conducted a study to determine the battery lifetime in a beacon or tracker application. Typically, these kind of devices operate from tiny coin cells with a very small capacity and low current supply capability. In this study, a CR2032 coin cell with a capacity of only 225 milliampere hours has been used. A tracker or beacon sends out so-called non-connectable advertising packets. Each packet contains up to 31 data bytes in Bluetooth 4.2. These packets are sent out in a certain interval, which can range from 20 milliseconds to 10 seconds. In this study, an interval of 5 seconds has been used. Also, Bluetooth mesh communication is based on advertising packets. Hence, the result of this study can provide some useful insights on the power consumption and battery lifetime that can be expected from a mesh node. In the diagram on the left-hand side, you can see the measured current for sending one advertising packet. As you can see, the power consumption between 4 and 6 milliseconds is dominant. This is when the data is transmitted. The ultra-low peak current consumption of only 3.3 mA in the transceiver helps to cut down the overall power consumption tremendously, and hence leads to an average current of only 2.56 microampere. The result? A whopping 10 years operation using a coin cell battery. In cooperation with our Bluetooth module partner Panasonic, we are delighted to be able to offer our latest all-inclusive and comprehensive developer board for our Bluetooth 4.2 chip. This board in a USB dongle form factor can be easily plugged into a spare USB slot of a PC. The USB port provides the necessary power supply for the board and allows communication to the onboard J-Link chip. Once connected, it allows the user to develop, run, and debug code. Furthermore, the general purpose I/Os of the Bluetooth chip are accessible via breakout headers. This allows developers to easily connect sensors or other devices to the Bluetooth chip. Thanks to the large on-chip RAM of 83 kilobyte, user applications can run on the embedded ARM Cortex-M0 core. Depending on the application, this may make an additional MCU unnecessary and hence comes with a lot of other benefits such as cost reduction. The versatility, completeness and easiness makes this board an ideal platform for rapid prototyping. On the left-hand side of the board, you can see a little silver box and a tiny blue chip antenna, which is the Panasonic Bluetooth module with the part number PAN1760A. Once there is a move from prototyping to productization, this module can be reused in the final end product and hence eliminates the cost and effort involved in antenna design and Bluetooth certification. Especially the latter can be significant depending on the Bluetooth SIG membership status of your company. The development board itself can be purchased via distributors using the given part number. Beginning of the year, Toshiba unveiled its latest Bluetooth LE5 controller with the part number TC35680. The focus on this product is on extended reach, which is essential for applications like home and building automation and asset tracking. Longer reach is realized by several enhancements. First, the receiver sensitivity has been drastically improved. While the previous generation of the IC achieved a receiver sensitivity of -93 dBm, the new generation achieves up to -105 dBm in 125 kilobit per second mode. This contributes directly to the overall link budget. Secondly, the transmitter output has been increased from 0 dBm to +8 dBm and therefore may make external power amplifiers obsolete. Toshiba continued its tradition of implementing optional Bluetooth features of a new version of the standard. Up to Bluetooth LE 4.2, the only supported data rate is 1 megabit per second. Since Bluetooth 5, there are 3 optional data rates. The feature LE2M-PHY adds support for a higher 2 megabit per second data rate, and the feature LE-coded PHY adds support for 2 lower data rates, which are 500 kilobit per second and 125 kilobit per second. In the lower data rate options, bits are coded into multiple symbols and forward error correction is introduced. By this, the receiver sensitivity and hence the reach is further improved for a given transmitter output power level. Coded PHY is therefore an important component for long-range communication. Even though the new Bluetooth controller drastically improves the physical area that can be covered, the power consumption has been kept very low. The peak transmitter current is only 11 milliampere at plus 8 dBm output power, and the peak receiver current is only 5.1 milliampere. Another important feature is the early advertising extension feature, which increases the payload per advertising packet from 31 bytes to 255 bytes. By this, the message broadcast capacity via connectionless advertising channels can be increased by a factor of 8. One improvement that is relevant for mesh is high duty cycle non-connectable advertising. Mesh makes use of non-connectable advertising, and in Bluetooth 5, the minimum interval time between advertising packets has been reduced from 100 milliseconds to only 20 milliseconds. This reduces the latency and increases the responsiveness and throughput in a Bluetooth mesh application. Last but not least, the embedded true random number generator meets the criteria as published by the National Institute of Standards and Technology, or NIST for short. This enables customers to develop products that are NIST compliant, which became a necessity in many high-tech industries. As mentioned before, the new Bluetooth 5 feature LE Coded PHY introduced 2 lower data rates and adds forward error correction. By this, the receiver sensitivity improves from minus 94.5 dBm in 1 megabit per second mode to an enormous minus 105 dBm in the 125 kilobit per second mode. In conjunction with a maximum transmitter output power of plus 8 dBm, the link budget amounts to a whopping 113 dBm. By using directed antennas with a positive antenna gain, the link budget could be increased even more. Even without considering any antenna gain, Bluetooth signals can travel up to 1.3 kilometer or 0.8 miles in an ideal space. This enables usage of Toshiba Bluetooth 5 devices even in agricultural and utility applications. In other applications like home and building automation or factory automation, such large distances may not be required. However, the additional link budget margin is still very useful to make message transmission more robust and to pass more obstacles like walls. So we nearly reached the end of this webinar, hence I would like to take the opportunity to summarize the key aspects. The core values of Bluetooth Mesh are: first, global interoperability. This is achieved by a full-stack solution, mature test and qualification tools, a long history of interoperability events prior to publication of the standard, and immutable models that never change once published. Second, reliability. This is achieved by multipath communication, the elimination of a single point of failure, a self-healing network, and a distributed control scheme with the ability of direct node-to-node communication. Third, scalability. There we talked about 2 aspects. One aspect is scalability in terms of nodes in a network, which can go up to 32,000. The other aspect is the scalability of the physical area that can be covered. Messages can be relayed up to 127 times. Fourth, security. It is achieved by mandating implementation of all security features, multi-layer security through separate device, network, and application keys, secure provisioning over an unsecured channel via ECDH, protection against all known threats, and last but not least, encryption and authentication of all messages within the network. As for Toshiba Bluetooth LE solutions, we offer two controller ICs in conjunction with our Bluetooth Mesh software stack. The current mainstream controller for Bluetooth 4.2 provides ultra-long battery operation due to its industry-leading low peak power consumption. Furthermore, due to its high integration, a minimal bill of material can be realized in combination with fast time to market. With our latest Bluetooth LE5 controller, we additionally put emphasis on long-range communication by supporting forward error correction and improved receiver sensitivity and a high maximum transmitter output power.